Welcome to your new unit. And the new unit is on fields. And we start off with section 6.1 on gravitational fields. And for our introduction to gravitational fields, we must consider what was happening a few million years ago. A few million years ago, tiny gravitational effects between particles began to draw matter into slightly denser configurations. Okay? And from there, in turn, these slightly denser configurations exerted greater gravitational force and this resulting in more mass joining, well, let's spell that right, joining the newly forming structures. And then these newly forming structures exerted more gravitational force, etc. What we had was repetitive and continuous gravitational effects. And all of this, what did that end up doing? Well, all of this formed what we now know to be our galaxy. And really what happened as well by forming this new galaxy, we could also analyze and study the universal law of gravitation. And this is hugely important because it gives us a really important result. The universal law of gravitation showed for the first time that the laws of physics apply to all objects. And what the universal law of gravitation tells us, let's say that we have some mass m1 and some mass m2, and that their distance between the center of each mass is given by r. What this tells us, the universal law of gravitation, is that there is an attractive force on mass 1, let's call it F1, and that is due to the second mass, M2, which has an attractive force as well. So an attractive force on M1 is due to the second mass, and it points from the center of mass 1 towards the center of mass 2, and there is this force of gravitation between the two objects. Mathematically, Fg, and that's a capital G in this case, this is our gravitational force, is equal to G m1 m2 all over r squared. G is our gravitational constant. And it is equal to 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared. And M1, M2 is the mass of each object. And R is the distance between the centers of each object. And we were able to calculate this universal force of gravity, this force of attraction between two objects, relatively easy following this equation here. So let's suppose that we do in fact have two spherical asteroids. One with mass m1, 1.0 times 10 to the 20, and the other one with mass m2, 3.0 times 10 to the 20 kilograms. And that the magnitude of the force of attraction between them is 2.2 times 10 to the 9th newtons. So we list off everything that we are given first. And that we have the force of attraction between them from universal law of attraction, and that is 2.2 times 10 to the 9 newtons. For any type of question like this, the force of attraction is given. We know that gravitational constant newtons, kilograms squared, meter squared. I had it backwards on the other side there, I believe. No, I have it backwards now. My apologies. Meter squared, kilograms squared. And we are asked in this case to figure out the distance between the two. So we have that our force of attraction between the two is given by G, M1, M2, all over R squared. We need to solve for R in this case. Well, that's simple as taking R, we'll have G, M1, M2, all of that will be divided by, because we would have R squared over here, that would be divided by FG, and we would have to take the square root of everything to solve. So that will be equal to 6.67 times 10 to the negative 11. We would also have 1.0 times 10 to the 20, and we would have 3.0 times 10 to the 20, and all of that must be divided by 2.2 times 10 to the 9 and square rooted to calculate the distance between these two asteroids. Make sure that you do know, and I'm going to put a note, on your calculators, know your scientific notation button. Most times it is seen as either an EE or times 10, sometimes the Y, or sometimes EXP. Those are usually the key scientific notation buttons that we see on a calculator. If we were to calculate this, my answer that I get after taking the square root, 3.0159 times 10 to the 10. I see in my question two significant digits, 3.0 therefore, times 10 to the 10 meters is the distance between these two asteroids. When we're talking about Newtonian gravitation, we're talking about force of attraction, universal law of attraction. What we also need to think about for 2 minutes are what's gravitational fields. And I'll move this up in a second. And let's suppose that we have some spherical object. And we're going to assume a spherical object in this case, which I'm just going to draw as follows. Every single spherical object has some kind of gravitational pull. And what all of these gravitational pulls do towards the center of this spherical object is create a gravitational field. And this gravitational field is a collection of vectors one at each point in space that determines magnitude and direction. And with this gravitational field that is created, and whenever I hear gravitational field, I'm very much reminded of like Star Trek, that's stating how old I am. We also get a gravitational field strength, which, by the way, is not that old. I am only about 31 years old. But I was a huge Star Trek fan. Going off on a tangent right now as I write gravitational field strength. The gravitational field strength is the magnitude of the gravitational field vector at a point in space. And it is quite simple to calculate the magnitude of this gravitational field. And we combine both the universal law of gravitation with Newton's second law, and this is the fact that we know that our net force is equal to mass times acceleration. Well, in this case, this is a force of attraction. So that tells us that Fg is equal to mg, mass and acceleration, or acceleration is gravity in this case. So when I'm looking at this m here, that is the mass of the object multiplied with our gravitational field strength g. And we know that Fg is g, m1, m2, sorry, this should be F of the object, and that will be all over r squared. Well, we have masses of the objects on both sides. So this tells us, we can cancel those out. In solving for g now, we get that g is equal to g m1 all over r squared. And typically this m1 is the mass of some planet. So the gravitational field strength on some planet, because really, let's think about it, spherical object. So g, mass of the planet, all over r squared. With r squared being, in this case, the radius of that planet. So, let's say, take Saturn for example. With a radius of 6.03 times 10 to the 7 meters. And the mass of the planet is 5.69 times 10 to the 26 kilograms. We're looking to find out the magnitude of that gravitational field strength. We're looking for g. So quite simply, our field strength magnitude on Saturn is equal to g, mass of Saturn, all over r squared. So that will be 6.67 times 10 to the negative 11 times 5.69 times 10 to the 26. All of that must be divided by the radius of 6.03 times 10 to the 7th. And calculating that on a calculator, relatively easy, we get 10.438. Let me look at my significant digits. 3 significant digits, 3 significant digits, so 10.4 is the field strength of Saturn. And there I forgot my units, that would be 10.4 newtons per kilogram would be the field strength. And how does that compare to the Earth? Well, let's think about that for a second. G on Saturn is 10.4. On Earth, the value of G is 9.81. How would we compare those? Well, quite simply, we would take 10.4 all over 9.81, and we would get 1.1. That is how many times more the magnetic or the gravitational field strength is on Saturn than on Earth.